Hope that everyone can see my screen okay. Maybe Jake, since you're the only one I can see, give me a thumbs up if you can see my slide. Awesome. Well, we're here today to talk about an exciting topic. It's one we get a lot of questions about as far as how Fluree scales. So those of you familiar with Fluree know that Fluree has this ability to have unlimited linear scaling for queries in particular. And so there's a lot of questions as to how that works, because it doesn't sound like that should be something that's easy or possible, or certainly something that people see in most other database architectures. So we're going to dive pretty deep into that, not all the way to the bottom, but I would say, at least halfway deep into exactly how the architecture works, why it scales the way it does. So when we talk about scaling to the edge, that can mean a lot of different things to a lot of people. It's one of those buzzwords you hear a lot. So what does the edge mean? Here's a couple things that people may think of. It might mean really close to your compute. Data scientists, people working on AI applications always talk about having their data by their compute just to keep things fast and speedy. When you think about the edge, you might think of a CDN, a content delivery network, things we've been using for ages to scale out web apps and websites across the globe, serving content or data geographically close to people. That might be what you think about. It might be a multi-cloud deployment. You're utilizing, or it's being utilized across Google and Azure and AWS. The edge might be inside of an app server. We call this database as a variable. This is a cool thing we'll talk a little bit about. That might be what you think about. Or the edge might be a web browser. You might have millions of users running web apps accessing it. And when we're talking about the edge, we're talking about all of these things. So Fluree enables edge deployment in every one of these scenarios. So for our agenda, we'll just really hit on 3 high-level things, but each will take a little while to get through. I'll be the quickest in the first part, which is just a quick introduction to Fluree. For those of you who are already or not familiar with Fluree and what it does, we'll just sort of set the stage, and that'll allow the rest of the discussion to happen seamlessly. We'll talk about our scaling architecture and how that architecture does scale. What's happening with the data is things are changing within the data platform. And then Jake, who's on the call, is going to actually run a live demonstration to look at a auto scale deployment. It's going to actually look at and talk about a number of things that we'll kind of walk through and discuss all in a single demo, so you can see what this looks like live. So quick overview of Fluree. Fluree is a data platform. It's really designed for what we call data-centric architecture, an architecture that looks more like the diagram on the right here, where data itself is a strategic asset, and there's many consumers of that data, many applications, et cetera. And that's in opposition to what we're used to seeing, and really what we've been building for 40 years, which is, or longer, an application-centric architecture that we see here on the left, which is someone's building an app, and then the database only exists really to persist state specifically for that application. And that leads us to some of the problems we have now in strategically leveraging data. It's because our data was, designed by app developers who were really just trying to solve apps, and so there's no real semantic meaning across the sets of data. They're all very proprietary to the app, even though they might be holding common pieces of information about customers, for example, might be across many applications, but every place it's stored in a different way that app developer happened to decide to store it. And we turn to technologies like data lakes to try to address this problem. But it's a problem that doesn't need to be addressed if we really had a data-centric view, because we're semantically structuring data so it can be automatically understood by other machines. We're enabling it to be connected, and we're enabling it to be secured at the source. So just to kind of highlight some of the differences, the application-centric versus data-centric. One is the interaction model. So an application-centric, the data interacts only with one thing. So it's a one-to-one model. It interacts with the app that sits in front of it. So it doesn't have to do a whole lot. In fact, it probably doesn't even have to be secured because the app in front of it's securing things. But when we get to a data-centric model, it's a many-to-many paradigm. Many different people updating data, many different people or apps consuming data. And it brings a whole new set of requirements to it that you didn't even have to worry about in a traditional data model. Security, the next line item here, you know, in an app, one-to-one app-centric model, it's written in custom code. It's in Java or it's in JavaScript or some other, or Go or some other language. And of course, it requires an application developer to understand what that security is because they need to know how to read the code that's enforcing that security. And that's okay, because again, there's only one thing talking to the data, and that's the app. So it doesn't really matter where the security is for the data. It can be in the app since that's the only way to it. Of course, the problem comes in when you do approach a data lake or data warehouse and you're ripping the data out from the back end. There is no security with the data. So it's one of the challenges data lakes and data warehouses continue to have. But of course, in a data-centric world, we want the security co-resident with the data. So we don't have to re-implement the security model with every touch point for that data. Capacity, you know, centralized versus decentralized and dynamic. Of course, as we talk about, you know, data analytics and AI in the traditional model, you're going to your traditional tools like ETL tools, data lakes and data warehouses. We're in a data-centric world built on top of these semantic standards. It's native. You know, you can dynamically combine data, even in a single query, you can combine data across multiple data sources. And it's again, because the machine is, the data is described in such a way that machines can understand what that data means automatically and combine it with other data. And as we look at external consumption of that data, you know, in our application-centric model, we're sort of to our love-hate relationships of building custom APIs to allow anyone access to that data. And of course, the cost of API development is enormous. You know, it's not that bad for you when you build the API, but it really puts a huge burden on your data consumers because they have to now write custom code to your custom API. And of course, the more APIs you have, the more this balloons. And the more we inevitably, you know, not intentionally, but inevitably open up security vulnerabilities. We're in a data-centric world. Again, we can just natively expose that data more freely because it is permissioned at the source. So when we look at the Fluree data stack to enable this, we look at it in layers. And I won't get into all of these individual pieces here today and this for the sake of time, but we've covered this extensively in other webinars. The first, of course, and the foundation is trust. So every piece of data that is ever stored is always cryptographically locked. It's provable. You can demonstrate that that data has never been changed in the future. You can always prove who changed that data, what else was changed. So everything has provenance at its core. Whether you care about it or not, it's just there, right? It's not going to get in your way, but it's there if you ever need it. We layer this with semantics. Fluree sits really on top of the W3C semantic standards for graph. Fluree exposes its data as a graph database, but it is a multimodal database. So you can issue SQL queries, you can issue GraphQL queries. You don't have to know the Sparkle query language, which is the standard query language for semantic graphs, although I would encourage anyone to learn it because it's immensely powerful. And then of course, security, we use smart functions in Fluree to allow data to defend itself. The security is co-resident with the data, which again becomes a necessity in this many-to-many world, many consumers, many producers of data, and we need the security really at the data source. Time, so because we have this ledger, this log of time, and really important also for collaborating around data, we can lock in time. Every moment in time of your data is instantly available. Sometimes we refer to this as having like Git source control, but for your data. So the data itself can be forked. You can get back to every moment. Every sort of commit is a transaction, which has its own hash that's traceable, for example. So this allows, again, in a many-to-many world, you may have many different systems trying to collaborate on data. Well, a traditional database, you can't even do that because it's constantly changing from underneath it. So how can two things possibly collaborate on something that's never staying the same? Time becomes important. And then, of course, sharing. Sharing is where you sit on top of all these layers and can share provable data, secure data, so you never leak any information, but also, as I mentioned, in a multimodal way. So SQL, Sparkle, GraphQL, these are all ways that you can get directly into Fluree. All right, so now to the meat of this topic. And by the way, if you have any questions, feel free to ask them in the questions chat. Ask them anytime you have them. I might end up answering them as I'm going through some of these slides, but I'll be going through those at the end after Jake does his demonstration. So one of the keys to Fluree scalability and one of the challenges to scalability of other data platforms is that they look at a database as a single thing. And whether you need to scale the reads or scale the writes, it's all locked up together. It has to scale together. So you're always scaling to the thing that is the most limited resource, even if you don't need to scale other things. And then it inextricably locks these two actions and actually creates scale limitations as a result. Fluree completely separates the notion of a query server, the database, if you will, the place where you go to get questions answered, from the ledger. The ledger is where this, very secure record of data and changes are happening and being validated. So I'll walk through the different ways of deploying Fluree because there's a lot of different sort of options here. And I recognize that especially people who are just getting introduced to Fluree, sometimes these options aren't fully clear. So we'll try and kind of walk through what they are. And I'll walk through just a simple, how do you interact with Fluree if it's running as a single server? And then what happens if we're going to actually start to scale those servers out, those query services? Then how do we scale the ledger or the write side out? And then should you want to take Fluree to fully decentralized model, which is something Fluree does, how to do that as well. So your first choice is how to deploy it. So Fluree can sit and be deployed, the service, in really one of three ways today. One is it runs right on the JVM. So anything that runs the JVM, you can deploy and use Fluree on. The second is you can use Fluree on demand, which is us. We actually host a cloud version, and you don't have to deploy it at all. You can just connect to it. And the third is we have a Docker container of this, so you can just spin up a single server in a Docker container. Either way, it's running on your machine. The other choice that you have to make, or you don't have to and on demand because we make it for you, is where you're going to store the data. And Fluree has a pluggable architecture for data storage. We have three currently supported methods. One is file storage, just on the disk of the machine, which is the default. You can also fully run Fluree in memory. It's more useful for testing or very short-lived operations. And we also support cloud storage. Cloud storage has some neat advantages. It's neat to actually have a database that can store its data in the cloud. It does slow things down a little bit, but for most workloads, it's plenty fast. So that's another option that you can choose from. But by default, when you install and run Fluree, you're going to just be using file storage, which is what a normal database would use. It would use the file system on the server that it's on. And then how do we start building apps that access that data and transact data? Well, in a very simplistic sort of single server model, I might be building a web app like a React application or a Vue or an Angular application. And Fluree exposes HTTP APIs where you can issue GraphQL queries, SQL queries, Sparkle queries, or what we call Fluree QL queries. Any of them, they're all active. And the data is always returned as JSON. So it's very easy to parse through that data. You don't really need like an ORM solution to kind of do all the translation you would with a normal service. Another real neat thing about Fluree's architecture is, again, this database is independent and scalable. We actually have one that runs in JavaScript. So I could be building that same React application and do away with the HTTP APIs altogether and actually literally run the database inside of the web browser. So the Fluree database can be encapsulated. We have actually a React wrapper around it right now where it allows React to query the database running in the browser that's running as a web worker right within the browser. And then this green line represents a socket connection that kind of sets up to that ledger server, and that's how it's going to get updates. And actually, you can build a real-time application directly in React using Fluree running directly in the browser. And you get all the permissioning and real-time sort of apps for free. It's pretty cool if you haven't seen it. Because it's JavaScript, we can do the same thing with NodeJS, where you can run the database inside of your NodeJS application. In fact, the demo that Jake is going to show is he's going to scale up Fluree query capacity, but he's going to do it inside of his custom Node.js app server. But again, the app server is actually running the database inside of it. So we basically have a Node.js database at that case that we can scale up capability. And then this would have other clients, other web apps that are connecting to it for its data or its own custom APIs. For that matter, you don't have to run Fluree inside of the Node.js app. You can use the HTTP API, and that's perfectly fine to do. We currently have support for Clojure for you to run the database inside of a Clojure app, if that's what you'd like to do. We're also working on making this available to all the JVM apps or programming languages. Or you can write any typical app server, Python, Ruby, whatever you happen to be writing. And again, just use the HTTP APIs. So any of those are options. And then if you want to start scaling your query server in a very simple capacity, instead of having those connect to your ledger server, we can now set up a dedicated query server whose only job is to satisfy queries. And by the way, you can scale these up as far as you want. So as many of these as you want to dynamically scale, you can. And these can also be daisy chained. So I could have these 4 query servers, and then I could have another layer of 50 query servers talking to the 4 query servers, and then my apps talking to those 50 query servers. So you can scale up and fan this out. Everything just keeps relaying messages upstream. On the ledger, the write capacity, we also have this ability to scale that out. So we do that in what we call a transactor group. So we call these ledger servers transactor servers. And what a transactor group does is it starts sharing information and state, and they work as a single unit. So now my query servers can connect to this transactor group. And in fact, they're smart enough that when they're connected, they're obviously going to end up talking to just one of these servers. But if that server ever goes down, they'll immediately try to connect to the other servers. So these query servers end up effectively having this load balancing built in. You don't even need to put a load balancer in front of it to do this. You just give the query servers, here's my, in this case, 3 transaction servers or ledger servers, and it'll automatically connect to ones that are healthy and alive. The neat thing is that these transaction servers, these ledger servers, have the ability to know who else is online and who's available to do work. And they start distributing the work amongst each other. So if you have many different ledgers and you're running them across 3 servers, effectively, they're going to dynamically balance the ledgers and the transactions that are coming in across those 3 servers. And if one of those servers goes down, that's fine. It'll rebalance the work to the 2 servers that remain. And then if that server comes back, they'll rebalance the load across all 3 of those servers. So they're always working to scale up. Now, unlike the query servers, which quite literally have no limitations of scale, you can scale it, millions of servers, and each server could be taking millions of queries. So there's truly no limit on the query side. Fluree has very strong transactional guarantees. We have full what we call ACID guarantees. And that does impose some limit of scale on the writes. So even though you can launch multiple servers, eventually you do get to a point of diminishing returns on the transaction side. So if there is a limit to scale, it's here. It's how many writes can happen. That's balanced as well, though, with the idea that Fluree is storing the data as a semantic graph, which allows queries to actually query across multiple ledgers. So it has this basically built-in sharding capability where the queries themselves can be sharded and can hit multiple services. So there's always an option of running many different ledgers that are being combined dynamically as though they're a single server. So if you do need to scale out that way, you can. It's effectively a shard scaling, but it's a more standardized way of sharding. And then very few people do this, but Fluree has the ability to decentralize the decision-making, the transactions. And this would be across multiple organizations, or it could be across, which are effectively sharing the same ledger. It could be across just multiple departments inside of a single organization. So any of those are options. And what it does is it starts communicating with other groups. We use at the core the Raft protocol, and it basically means that once more than 50% of the decision makers agree that a transaction is valid, it then becomes committed and part of the official record of transactions that happened. So that communication needs to happen, and even if you have a single slow server, it doesn't really slow things down because again, all it needs is over 50% of the sort of participants to agree that a transaction is valid to move forward. But it does slow things down because now we need to wait until at least 50% of the server clusters do agree. So there are trade-offs to going decentralized, but if you have a situation where you have independent entities that truly want to run a common database together, Fluree has the ability to do this. In fact, it's the only product I'm aware of in the market that has the ability to do this. All right, so let's quickly dive into the meat. So how do we actually have these high-performing in-memory database engines, these query servers? How do we make that scale as things in data is changing in a dynamic database? And we're going to start first by looking at how the data actually sits within Fluree as these records are happening. And we're going to start with effectively the core of how every database that I'm aware of stores and manages data in some form of another, which is what's called a B tree. A B tree is a balanced binary search tree. And it's a way that databases or lots of things utilize to quickly find information without having to look at every piece of data until it finds a match. So it can get to the data it needs very quickly. And this is, of course, important for things like query speeds. If we want queries to respond in a millisecond or even sub-millisecond, we need to get to that data like immensely quickly. We don't have time to go through, potentially millions of pieces of data to find matches. So this is a extremely simplified version of a B tree, but what a B tree is it looks kind of like a tree, and it has branches, or the root, which is the top that we're looking at. It optionally might have layers in between, which we call branches, and ultimately the data ends up sitting at the leaves. And this is again a very simplified example, but we're just sorting people in this case by their first name. So it's alphabetically sorted. We see we have on the left, Alice, information about Alice and Bob, Jane, then Ken in the middle, and Mark and Sue on the right. And they're kind of chunked up into different areas so that we can just find data in the chunks quite quickly. And I'll explain this a little bit more as we go. One thing that's important, and Fluree uses RDF to store its data. RDF is a way of representing a piece of information, and RDF is a W3C standard. We extend RDF a little bit because we have time travel, and I won't get into how time travel affects these indexes today, although I do believe we did a webinar in the past on that, but it's a little bit too much for at least explaining the scale capability. But RDF is a very simple format, and any conceivable piece of information can be represented as RDF. It's standardized, and this is the foundation of really what allows different machines to dynamically understand data between different machines without having to have like ETL layers in between. All of these, it's often called triples because there's three pieces to RDF. It's what we call the subject, the predicate, and the object. And on the left-hand side for Alice, Alice is the subject, and you see it's repeated 4 times here. The next is what we call the predicate. It's sort of like the column in a relational database or a spreadsheet. And then the last piece is what we call the object in the RDF standard. And it's really the value of the cell. And in fact, all this data that we have here, if we wanted to look at it like it was a spreadsheet, this is what that data looks like. So we have the rows on the left, Alice, Bob, Jane, Ken, Mark, Sue. And then we have the columns on the top, is a friend of, is born on, identity, etc. And then we have the values for each of those cells. So one cell represents one piece of RDF. So that's kind of what RDF is. So Fluree is a log of RDF data. It's a append-only log of RDF data. In this case, we're looking at an index form of it. So now I have this data, it's controlled by the ledger servers. So again, the ledger servers are the only things that can update data. They're the only things that can execute writes. So they basically all have a consensus of what this is and how this data is organized. And now we spin up a query server. So we have one of these query servers on the left. Again, this could be running inside of a web browser. This could be a Dockerized query server container. It could be Fluree running inside of a Node.js app. It could be a lot of different things, but it's a query server. Effectively, we're spinning up a new database. And someone comes and connects to that database, or it might be the app, and issues a query. So what happens? So the query here, and I'm using a simplified sort of SQL format, they say select star from Ken. I want to know everything that the system currently knows about Ken. And since this query server is stateless, again, it just got spun up. It's an in-memory database server. It needs to start to figure out this information. So the first thing it does is it asks for the root, the piece at the top that basically has a layout of how to find all the pieces of information below, because it doesn't currently have it. Once that root is requested, it now sits in memory in the query server. It never has to ask for that root again. That root is there. Fluree provides a guarantee with all of these index chunks, all of these pieces of data here that will never ever update one. So at the point one of these chunks of data gets put up on the query server, we know it will never be updated. So part of this walkthrough is how do we end up updating this? Because ultimately transactions happen. So if we're not allowed to update any files or chunks, what happens? And that's really what we're walking through here. So now that the query server has this root node, and it knows that all data from A through S is contained somewhere below that root node, it knows that Ken starts with a K and it's somewhere in there. But now it also knows it needs to go down a level. And you see here the leaves each have chunks. And it can quickly tell that the chunk that has information about Ken is in the C through K, the middle leaf. So it's going to go ahead and ask for this. And then this chunk now gets moved into memory. Again, the next time this gets asked for, it's already there. It no longer needs to retrieve this. And Fluree is going to use up the amount of memory that the query server allocates to it. So you can actually specify how much memory it's allowed to use. And it'll eject things out of the cache once it fills up that memory. So you could say, you know, you got a gig of memory, Fluree, and Fluree will start to cache this data in that gig, or it could be 100 megabytes or 1 megabyte, whatever the case is. It's going to start caching these chunks of data. And now that we have that leaf data, we see the Ken is actually in there, and it's going to be able to return those results. It has everything it needs to return the results. So now the next query happens, and that same user says, well, I want to select star from Jane. Well, it looks at the root, but it already has that in memory, so we don't need to go and ask for it again. So that happens extraordinarily fast. And then J, it says, okay, well, that's in the leaf C through K. Well, we already have that in memory too, and it's able to get that data. It's able to do this at in-memory speeds. And in fact, if you've used Fluree in this capacity, a query like this, all these results will come back JSON encoded and formatted in under a millisecond. It's extraordinarily fast. And it's because it's sitting there in memory. But I have a representation of all the data that exists there. But again, I only have the pieces that I've needed. I've pulled them in memory as I've needed them. So let's do another query. Now we say select star from Bob. Well, we again need to look at that root node again. It's already in memory. We didn't have to go and get it. And now it's saying, well, B's it's in this leaf A to B. I don't have that leaf yet. So now it's going to pull that in memory. So now in the upper left, you see we have kind of 3 chunks sitting in memory. And of course, there's now the Bob data, and we're able to pull that in. So at a very simple level, that's all we're doing. I'm gonna move my zoom controls here real quick so I can see better. All right. So that's pretty easy. It's easy enough to understand. But what about transactions? So let's launch a different query server. It's maybe running in a different part of the globe, or might be in my own data center, it doesn't matter, but a different user connects to that. And now they're going to try and update information. So we launch this query server on the right now, and a user's there, and a user tries to add this information about Tom. So this is brand new information. None of the servers know about it. And assuming that this is valid, this user is able to add that data, and the data conforms, and all the smart functions in Fluree have passed, and the security passed, assume this data is allowed to come into the ledger. What do we do with it? Well, we can clearly see that where we want to put this data is in this lower right leaf that currently has L through S data, right? It should come right after Sue. But again, we're not allowed to update anything. Once we wrote out that data, we'll never, ever change it. So our only option at this point, you would think, would be we have to create a whole new index to do this. Well, that would be kind of inefficient. In fact, all the servers would have to wait until a new indexing job happened. So Fluree has another structure to handle deltas, the changes, and we call this novelty. So in addition to this cache that we've been building, we actually have this little side cache called novelty. And this Tom data we got is now broadcast out to all the servers, not as a new index, but just as a delta. And these will continue to collect these deltas until we fill up what we call the novelty threshold. This is a feature you can set in Fluree. So and these are set in size, like 1 megabyte might be your novelty threshold, and then 2 megabytes might be what we call your novelty max. So there's kind of 2 lines in there. Again, you don't normally have to worry about this. Fluree will set sensible defaults, but these are features that you can set. And basically, say the novelty threshold was set at 100 kilobytes, Fluree will collect deltas in this way until there's 100 kilobytes of deltas that have been collected. So that might be over 10, 20, 30, 50, 100, 1,000 transactions before it sort of fills that up. But only then will it kick off a new indexing job. And it'll kick that indexing job off in the background. So while the new indexing is happening, because of this model, we're able to continue to take more and more and more transactions. The reason we have novelty max is we want to be able to set some maximum amount that will hold in novelty before we do actually stop things. Because what we don't want to have happen is we don't want these query servers to be able to, or to ever be in a situation where they completely run out of memory. So we want to make sure we have an upper threshold. And if we ever do hit that upper threshold, Fluree will actually stop until the indexing job is complete and it can sort of flush out the novelty. But let's just say that this small transaction kicked off the process. In the meantime, everyone has the current data. It can very easily, all these query servers can very easily fold this kind of data change right in. But now the index process happened. We've updated the data. You see it's now at the bottom of the leaf. We now have a new leaf. That old leaf is no longer needed. It can be garbage collected. Again, we're not going to update the old leaf. It still exists, but now we have a new file that has this data. And because we have a new file, we also had to write a new root file up above. And now our user in the upper left says select star from Bob again. And we have a new root. So the server had to go get this new root, but you see the root still points to the original leaf AB and leaf CK. And because no data changed in those leaves, they're still valid in cache and they're still there in memory. The old root sort of file can be garbage collected. It'll drop off of the query server as it runs out of memory, etc. But this is the way that Fluree is able to always have constant updating, run indexing in the background, and with these immutable files, not have to remove basically database chunks frequently up to these query servers, and they can maintain these very fast in-memory speeds. So that was a simple example. Again, I mentioned that these trees can grow and grow and grow and become bigger. So we can add branches in between. And how Fluree actually ends up chunking these is that each leaf ends up holding 100 kilobytes of data. So we'll break up a leaf into 2 leaves once it exceeds 100 kilobytes of data that's supposed to be in there. It turns out 100 kilobytes of data usually stores about 3,000 pieces of information, 3,000 triples, RDF triples, or what we call flakes as we extend it. So every time you pull up one of these leaves, you not only have the data you were looking for, like Bob, but you also have all of the things very related to Bob. We try and organize data into these leaves based on data that's typically asked for together, reducing the chances that we have to get other leaves for subsequent queries. So we want these leaves to contain kind of logically similar information. And then once we have 500 leaves, we add a new branch. So this keeps building. Because we have these very wide branches, what it means is that in the upper left-hand side, we'll see how big a database has to be before we have to add another branch into the index or into the tree structure. So we can get all the way up to 50 megabytes database with 1 level deep. 2 levels deep, all of a sudden we're up to 25 gigabytes. 3 levels deep, 12.5 terabytes. 4 levels deep, we're all the way up to 6.2 petabytes of data size. And as you can see, this is exponential. Now, every time we add a level, it does slow things down a tiny bit, but generally about 10%. So there's just one extra hop to get to the data. So query might slow down about 10% over what it was. So instead of taking a millisecond, it might take 1.1 milliseconds to get that query result. So it's still very, very fast, but this is how it's able to scale to a lot of data. So I know that was an awful lot of information, but that is in the guts as to how we're able to have this scale at a large scale. And I am going to turn it over to Jake. He's going to show some of this in action, and then we'll get to whatever questions we have time for. Over to you, Jake.
Thanks, Brian. That was a great explanation of how the data gets stored and accessed with Fluree. That helped me learn a few things. I'm going to share my screen here. You able to see that, Brian? All right. I'm going to go through a demo today of some of the concepts that Brian brought up in his presentation. Generally speaking, this is what we're going to be building. We're going to start a ledger server running in AWS, and from the presentation, this would normally be considered all-in-one. So if you wanted to run everything on one server, you could here. I'm also going to spin up a load balance cluster of query servers that connect to the ledger server, and we'll show that these are able to scale out when we create a lot of traffic to the cluster. With another stack that I'll deploy is another bunch of ECS tasks to generate a bunch of traffic to the node cluster. I'll also show an event-driven approach to loading some transactions by hooking up a Lambda event listener to an S3 bucket that will send some data to our node app that's running as well. For the sake of time, I've already deployed some of these things because they take a few minutes to deploy. We can kind of get an idea already in the AWS console. This is our node cluster where we're running 2 tasks. I was messing with it a little bit earlier, so it actually scaled up to 4 and then back down to 2. But we're only running 1 task to create traffic for this. So before we do anything else, we're going to increase that because it takes some time for it to deploy and start to generate traffic. So we're going to come in here to our traffic generator stack. And by the way, I'm using Amazon Cloud Development Kit to create this infrastructure at AWS in our sandbox environment. AWS Cloud Development Kit will turn into CloudFormation scripts that get deployed with CloudFormation, but allows us to use code, infrastructure as code, to make those changes. In this case, I'm using TypeScript. And I'll share this repository with you after the presentation. So if you want to download this and deploy some of these resources to your own AWS environment, you'd be able to do so. So I'm just going to ramp up the number of these tasks to 50, and then we'll go in and do a CDK deploy of that stack. Just make sure it's not going to prompt me for anything before I move on. So essentially what we're going to do here is take one of these tasks and turn it into 50 tasks that start to generate load on our node client. So let's start talking about what we've built so far. So to start with, we created a let's see here. Make sure that's running. We created a ledger container using our, as Brian mentioned earlier, one of the ways to deploy Fluree is to use the Docker image that we publish to Docker Hub. And that's what I'm doing here is I'm creating a container task running directly from our Docker image that we publish, create a port mapping on it, and allow connections to our default port of 8090. And then the next step is we're creating this is the node query server cluster, which is using Fargate. And instead of using a pre-made image like before, the CDK app is actually building, bundling, and deploying the contents of this NodeJS folder right here. So that folder contains a Docker file that's very simple, coming from the node image that they publish and copying over an index.js file to it, and then runs node with that index.js file. So our query server cluster is running this index.js file, which is, I pulled from our Node.js example in our GitHub repository. But this is essentially running a query server in JavaScript with Node.js. So and then I started the cluster with 2 tasks, and I did max out at 20 so we don't run up our AWS bill too much during this presentation. And then also a couple of other things to point out. I made the memory and the CPU about as small as I could for an ECS task in order to be able to show a scale out event. Because if I made this normal size or bigger, it would take a heck of a lot of load to even trigger the scale out event in the first place. And then I also made the scale out target to be 30% of the CPU utilization on that cluster. So again, that's a little bit less than I normally would do, but I just wanted to make sure we were able to show that this would scale out. And then the traffic generator stack is just another Fargate task that, again, is using, we're using a container image from this repository. So the contents of that traffic generator folder, is another Docker file that's just adding this pinger.sh bash script, and all that's doing is running a curl command to over and over and over select star from our database. So we can go back to the console now and see that we have, oops, reload. We have 50 running tests now instead of 1. We're still running 2 node tasks. It does take a little bit for those to ramp up. Let's see, that's a ledger server. So now you can see our CPU is starting to spike, shoot up, and we've entered an alarm state so that our CPU is greater than 30. I showed you that's where we set that in the app for 3 data points. So this should be triggering now a ECS to start to create more tasks. So now you can see we have 5 pending query server tasks, and once they start, we'll be able to see the load start to start. It might not be enough. If it's not enough, it'll start some more tasks and some more tasks until the memory on average gets below 30 again. Another piece of our stack that I wanted to show you today too was this bucket, S3 bucket to Lambda event. And again, I deployed that already as well. We can go through some of the code and then we can demo that running. So what we're creating here now is an actual Lambda function with AWS, and the Lambda function is going to be the contents from this onboard Lambda folder that I have right here. And then all we're doing here is we're receiving the event, the S3 triggered event. That event contains some information that we pull out, the name of the bucket, the key, and then we have to actually get the object from S3 and pull it in, and then we can post that data right to Fluree. We pass in the URL with the environment variable with the ledger name to a transact. And here's an example where we're going to add data or post data to the Fluree ledger from a Lambda that gets triggered when an object gets loaded into S3. So we created a bucket up here, we created a Lambda, and then we add an event listener on that Lambda that watches for objects being created on that bucket. So what we're going to load is first, right now we don't even have any collections in our database. So I'm going to create a schema with a collection called eateries with some predicates like the zip, some notes, age, country, state, city, address stuff. So we're going to go over here to the bucket and upload the schema to the bucket. That shows that we uploaded it. And now we should be able to come in here. I copied this curl command, and we're going to do a post to the query server to select star from that collection of eateries that I created. And you can see it's an empty collection because we didn't actually add any eateries. So we'll go back here. Let me actually show you that file first. So here I just added a couple of eateries, a place called Tacos, 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 and Coffee Squared. So if we go back in here and upload that file to the bucket, and then that gets uploaded. And then we should be able to go back to the terminal here and run that same select star from eateries. And I can actually output it in a format that's a little bit easier to read. You can see that that went to our query server. The query server passed that transaction off to the ledger, and then when we query it from the query server, it exists in the data. All this is happening while we're creating a lot of load on our query servers, and now you can see we've scaled out to 7 from 2, and it looks like we're starting to stabilize. Oh, that's the memory. The CPU is coming down a little bit, but likely this will keep scaling up and up and up until we get down under 30, and then we'll be in good shape. So make sure I covered everything I wanted to. Yeah, so that's my demonstration today. I'm going to turn it back to Brian so he can start to answer some questions for you all.
Great. Thanks, Jake. That was awesome to see. And one thing I did want to clarify, I think it was really cool what Jake set up, which is this idea that transactions from Fluree, again, there can be multiple updaters. You know, a typical application-centric deployment, there's only one thing that ever updates the data, and that's the application sitting in front of it. But in this model, there could be updates coming from anywhere. It could be coming directly from your customers, could be coming from multiple different systems. And we allow transactions to be containerized, you know, cryptographically signed, containerized, and however they end up making it to the transaction server doesn't matter at all. So typically we would take a transaction and we would just issue like a post to the API endpoint and say, here's the transaction, and to the and if it was to a query server, it would pass that transaction back to a ledger server. Or if it was a ledger server we were talking to, it would take that transaction and process it. But it doesn't really matter how it gets transactions. Jake showed transactions coming because JSON files were getting dropped on an S3 bucket. And then of course that event listener was grabbing those data updates and then basically pushing them back. You know, technically a transaction could come over email. Again, transactions are all cryptographically signed, so we don't have to have as much control over the pipe which the transaction entered the system from. Transaction can enter from anywhere because we can validate the integrity and who issued the transaction regardless of how it got there. And I think that's a really, really neat thing to point out. And, you know, for those of you who have never seen Fluree work or issued a transaction might think it looked a little bit strange to be issuing transactions by dropping transactions to an S3 bucket. But in reality, that was just kind of showing off this capability. It doesn't matter where transactions come from. They can be independently validated regardless. So we'll get to some questions. There's a question from Rob that asks if there's any recipes or descriptions available how to, you know, deploy and run availability geared setup with multiple query and transaction servers on K8s. And the answer is yes, although I can't tell you exactly where that is, except we actually have a K8s folder in the source code repository that actually has K8s or Kubernetes deployments. So it's actually right in the GitHub source code control. So if you look at the ledger in GitHub, you'll see a folder there that has a bunch of K8s related YAML file, et cetera, that you can take and modify. There's a question about consensus, and is there an option of changing the Raft consensus to proof of stake or proof of work in a decentralized scenario? And the answer is yes. So it's not built, although the consensus protocol in Fluree is it is a protocol. It is pluggable, so it's able to support different consensus mechanisms. There's a a handful of basically methods that any implemented protocol has to be able to adhere to, and that's the only restriction. We actually have had even PBFT in Fluree. Very few people used it, and so we just haven't maintained that. So right now it's really just Raft, but absolutely capable of plugging in different consensus mechanisms. Again, they just need to adhere to the proper protocol. I won't say it's something that can be done, in a day or anything like that, but absolutely it's available. And we would welcome any contributions if there were any from the open source community for some of those. There's a question about storing images and file objects, and I believe how that relates to scaling. And I guess the first thing I would say is, like probably any database, whether it's MySQL or Mongo or Cassandra or SQL Server, the general recommendation would be is that if you have object storage blobs, that you don't store them in the database, you store them in object storage. So you're going to use S3, or if you're running this in more of a blockchainy way, you might use IPFS. But you're using object storage. And then of course, what's in your database is a pointer to that. One of the ways that's typically done, because Fluree maintains such integrity about the data that's in there, is to also help maintain the integrity about the object storage data and images. Normally you would store the hash in there as well. That way anyone getting the image can validate the hash matches, the hash stored and provable within the Fluree record. And of course, if you're using something like IPFS, it does that step for you automatically. There's a question about, will the code for this demo be made available? Jake, maybe you take that one.
Yes, definitely. Right now I have it marked private in our GitHub repo. I need to take a couple of things out, like our custom DNS names, and edit the README file, but I should have it later today or tomorrow published. I don't know, maybe Kevin knows how we can broadcast that link to everyone. But yeah, you're welcome to use the infrastructure code, and it'll run in whatever, if you're using AWS and you have your AWS configured on your machine, it'll deploy to that environment. Just be careful with the leaving it running. You probably don't want to have 50 or 60 tasks running. So you might want to keep note to destroy the stacks when you're done.
Yeah, you don't want a big AWS bill. And I'll just point out, I recognize it's the top of the hour, so if people need to drop, of course, go ahead and drop. We'll stay on at least for a couple more minutes here, because there's a lot more questions, and I'll at least try and get the ones that I think we can get to pretty quickly. So one of the questions was, if new servers are added, how does it affect the scaling? Does it affect it negatively in any way? And there's two answers to that question. So one is on the query side, the answer is essentially no, or it's so minimal that it's not very noticeable. If it ever were, you can always fan out. So the idea that if I had 100 query servers, and I felt like they were all connected to this ledger server for all the updates, right? All the events coming through. And if I felt like they were putting too much load on my ledger server, where my ledger server is now having a hard time processing new transactions, which is what it's supposed to do, I can always put a single query server in front of that ledger server and then connect the, I can't remember how many I said, 50 or 100 query servers now to that single query server. So now that query server is brokering all the work of all those other query servers. And again, not that it would ever be necessary, but you can do that layer on layer on layer. Other part of this question is, can this affect like losing data or becoming slow? And again, not in a noticeable way as far as slowness, and absolutely not as it relates to data. So Fluree is very strict about the architecture and adhering to the ACID guarantees. One of those is durability. And so there's a lot of work that goes into making sure something is durably stored, cannot be lost in any sort of scenario when it's written. And because all of the changes and updates are being broadcast out, but Fluree is an append-only log, it has this really internal notion of time. So if by the chance that something way upstream got an update, but it would be able to immediately tell if it got the prior update. And if it didn't for some reason get the prior update, it can ask for that. So talking about it in simple block terms, if you think about it going up in numbered blocks, right? Every transaction or multiple transactions is going to create a new block. Block 2, block 3, block 4, block 5. They're all getting broadcast. If for some reason a server got block 8, but the last block it got was block 5, it's going to immediately know that it's missing information. And what it can do is actually go and fill in those gaps before it does anything. So that should really never happen, but as you know, it's the internet, things can happen. So in the case it does, there's actually a built-in way for it to quickly rectify that. So there should never, ever, ever be any lost data. That's really the fundamental guarantee of Fluree. It will lose a lot of other things before it will ever lose any data. Here's a question: if data integrity is enforced through RDFS, I assume by RDFS it's referring to RDF schema. And the answer is partially. So the schema is just part of what's enforcing data integrity. The other parts that are enforcing data integrity are the smart functions, which allow really business logic to be incorporated in. We do have, and this actually kind of ties into the next question, which is related to OWL, which is a way of packaging RDF data, or actually more a way of representing taxonomies within RDF data. But we do have in the works a way of representing schemas in Shackle. And Shackle is, for many people, replacing OWL. It's sort of a little bit more focused on kind of closed world, typical database environments, as opposed to kind of more loose open world way that OWL is. So that is something that is coming here hopefully quite shortly. There's a question from David about addressing conflict resolution if transactions are coming from anywhere. This is a great question. So again, back to the ACID guarantees, and I guess I won't get into the full details here because that would take a while. There can never be conflicting transactions. In fact, transactions always end up having a very distinct order to them. And it's able to guarantee the integrity of everything in between. But then that also brings up situations like if I can't get a whole database to lock for me while I make some manipulation, how do I control that other transactions didn't change data in between my query and transaction, for example? We actually give a couple mechanisms of doing this. For one, Fluree natively supports right in the transaction a compare and set. So what you can do is say you had, I'll give two examples. This would be the harder way of doing it, but I'll give the easier way of doing it in a second. Say you had an atomic counter. So you're trying to count something in the database and you query for the current value of the counter. It says it's 100. And then you want to update it to 101, right? You want it one more. Well, what if between that cycle, somebody else already updated it to 101? You would be basically putting in the same data that they already have. It would no longer be an atomic counter. So one function that's supported directly in there is compare and set. So what you can do is you can say, update it to 100, but first check that the current value is still, update it to 101, but check that the current value is still 100. And if while it's processing, while it has basically that lock at that minute moment in time, if for some reason it's not 100 anymore, the current value, it'll throw an error for that transaction. So the transaction won't happen. And then you as the client decide what to do. Do you requery and resubmit, or whatever you want to do? And that situation is up to you. So that's the way you can control how data is changing if it's being changed simultaneously. A simpler way of doing that is another function supported is just increment or plus. So what you can do is actually issue a transaction where you never even tell it to make it 101. What you do is you say increment the current value, whatever it happens to be at the point this transaction is run, by 1 or by 10 or by 20. So you can actually programmatically control that, and the ledger will substitute in the current value. So you have a guaranteed something like an atomic counter. Lots of questions. This is great. So are there plans or supporting smart functions in JavaScript? It is something we would like to support. If you've looked at our smart functions, there's already even an option in there when you register a smart function of registering the language that that smart function is written in. So we've always designed things from the beginning to support multiple languages that smart functions can be expressed in. JavaScript is at the top of our list as far as the next one we would like support for. It's something that we're not actively working on, but I hope in the not too distant future, we will have that in place. What would be a near optimal ledger server cluster side? I'm not sure I completely understand that question, but the ledger server, as far as I think how many servers like should run for the ledger server cluster, if that's the intent of the question, that is somewhat dependent on the protocol. So Raft, given that's what's supported, at least in the current version of Fluree, I'll give the answer specifically for that, but it's important to note that different protocols have different sort of failure characteristics. So I'll give a quick example of PBFT as well. So Raft protocol, basically the failure equation for Raft is 2 times the number of failures plus 1 is the amount of servers that you want to have running. So if you want a ledger server cluster that can support a single failure, then it's 2 times 1 plus 1, which is 3. You want to be running 3 servers. If you want to run a ledger cluster that can support 2 simultaneous server failures, but still stay completely alive, then the equation is, 2 times the number of failures, which is 2, 2 times 2, which is 4, plus 1, 5. You want to run 5 servers. If you've used any other products that use Raft, so this might be like etcd, which uses Raft, or any of these, some of the databases, more databases are using Raft, you'll see that they, along with us, would tell you never run 4 servers, either run 3 or run 5. Or if you have to, run 1 or 2, but 3 is an optimal number, 5 is potentially a little bit better because you get up to 2 failures. And that's because due to that equation, 4 servers buys you absolutely nothing but effectively latency and more failure points, because you can still only sustain a single failure in a 4 server cluster, the same as you could in a 3 server cluster. So why add the additional overhead? Either go from 3 to 5, et cetera, in that. Now, again, PBFT, the equation is 3 times F plus 1. So in a PBFT cluster, to sustain 2 failures, you would need 7 servers, whereas in Raft, you only need 5 servers. So again, that's where consensus mechanisms become an important component to answer that question. There's a question about deleting history. Is it possible? So there's 2 parts. One part of Fluree, which we actually didn't really represent in this topic, is the core ledger itself, the core append-only log. And that always exists. What we kind of walk through in my slides walk through was actually one of the indexes. And we maintain multiple indexes. This is what allows us to answer queries in a millisecond, is the indexes have the data organized in a way to quickly do queries. Obviously, in append-only log, to answer a query from that, we would have to read the entire log. So it would potentially take a long time. So that log always retains information, but you can always delete data, and it's deleted as of that moment in time. And in that index, it doesn't exist for that moment in time. But historical moments in time, it still exists because it did exist at that. We have currently in beta, but it's available in the current version, a capability called, I forget what we call it, but it allows you to, I think, purge. It allows you to actually purge data even out of the ledger side. Although we don't allow you to do that without any sort of trace, we basically end up creating a new transaction that purges the data, that references that where the data used to be, but it's now gone. And it also has the cryptographic proof of who did that. And then that becomes part of the new ledger, but that will allow data to completely disappear in Fluree. We use Merkle tree hashing to sort of build up the ultimate hash that the ledger is. And basically the implication of deleting data is that because of the Merkle tree structure, we're still able to prove out all the data that exists in the system, even though some data was purged. Hopefully that answers your question. There's a question about the protocol for ledgers to push updates and something about a Python app. So the updates are pushed today in a WebSocket, and they're really pushed in a format that is specific to Fluree query servers, that it can quickly grab that data and again kind of fold those deltas into, you know, its current in-memory database. It can be listened to by other apps, but it's not really designed to be consumed by something that isn't a Fluree query server. We actually have a feature in the works where we're doing something that more generically represents that data, so it can be consumed by any app. So any app, like a Python app in your example, can actually open up a WebSocket connection and get a real-time events of everything coming through. There's a question about what flavors of indexes are supported: subject, predicate, object, etc. So there's a section in our documentation under the architecture section that talks about Fluree indexes. And we actually maintain 4 different indexes. And it turns out any query you ask can be satisfied by 4 different indexes. The key is figuring out, based on the query, which index is going to most efficiently be able to answer a particular component of a query quickest. And that's part of just kind of the underworkings of optimizing queries for these speeds that happen. But there's 4, and they're actually labeled, you know, you say subject, predicate, object, which is the names of the RDF spec. They're actually labeled SPO for it's ordered by subject, then predicate, then object, then T, time. So we have a spot index, we have a PSOT, which is predicate, then subject, then object, then time. That's actually allows Fluree to act like a column database. So it's using the predicates or the columns as the first part of the sort. So I can quickly find everyone that has a first name, for example, whereas the former one, I could quickly find everything about Bob, like the example I had shown. We also have a POST, which is predicate, then object, then subject, then time. And this allows you to say, okay, find, you know, where first name equals Bob. And then we have a OPST index, and this allows reverse graph crawls. So those 4 indexes effectively cover any sort of query scenario, and all 4 of those are always maintained in Fluree. There's a question, does a query server have to have access to all the data in the ledger, or can it be limited? Great question. Actually, when a query server connects to the ledger, it connects as an identity. So if that identity is basically a root identity, then it will see everything, but it can actually connect as any identity, and it might already have the data filtered that comes to it. And that becomes really interesting because then other query servers might connect to that query server that already has a filtered set of data. But it actually allows this sort of layered filtering capability for permissions and access, which is kind of cool. Yeah, good question. Anything that connects to a ledger server is going to connect as an identity. Usually, if you're running the query servers yourself because you're trying to scale out query for your own apps, those query servers will connect as a kind of a root user. They'll have visibility to everything because the things that are connecting to them will then allow that filtering to happen based on their identity. But yeah, they can connect as an identity. I'm trying to get through. I think we will stop there because I think the rest of them are going to require a little bit more time to explain. But we're happy to take any questions, you know, on our Slack channel if you'd like to ask a question there. And I really appreciate there's still a lot of people online, so appreciate you all hanging on for some extra Q&A time. Thanks, everybody. This is going to be recorded, so we'll have some information out about that. And then we'll also include information, as Jake was saying, about the code repository that Jake used for his presentation. Appreciate everyone. Thanks. Till next time. Bye.